Okay, so I think we can start now. Just before starting, I will give you a brief introduction. So today we are going to talk about modeling of existing reinforcing concrete structures using OpenSees and STKO. Now, before starting with the webinar, I want to show you some news because we've been updating our website. So in the meantime that we wait for other participants to join, I'm going to share my screen and I want to show you some updates. Okay, so first of all, we are redesigning our website, and something that I want to show you is this basically. If you go on our website and you go under product and STKO, you will find this updated web page. Here you can find everything, a short presentation on STKO. So what is STKO, why STKO is so innovative, a link to the training, so e-learning courses and support forum, and many other things. And one important thing is this one now. Since we have been updating to OpenSees 3.2.0, which is the latest OpenSees version, we decided to compile a command list. So everything that we have for OpenSees 3.2. So if you go here, you have a document, and this document will be constantly updated. And here we have a list of all the components that we have in STKO by category, and what is the counterpart in OpenSees. As you can see, for most of them, the correspondence is 1-to-1. So basically, we support everything that is in OpenSees. Sometimes you will find some notes. For example, this one is something that we are going to talk about today. For example, here we have an element in STKO, which is called Reinforced Concrete Joint Model 3D Element, which is not available in OpenSees. But there is a note. For example, every time you see something like this, basically what it is an automation of STKO. What is that? So for example, you go on note 1 and you will find the description for this. Note 1 should be on the bottom line. No, should be on the top. Let me go on the top. So basically, something like this, for example, is not available in OpenSees as it is, but it is an automation in STKO. What it means is that STKO give you the opportunity to create, for example, in this case, a joint, which is nothing but a macro element, and STKO automatically will create all the components for OpenSees. Now, I will explain in details what it is today, but there are many of them. In other cases, you may find some other nodes, for example, new shell elements, which are shell elements that we developed and we put in the OpenSees source code. And in this case, you see another node here. But for most of the elements, there is a one-to-one correspondence with the OpenSees element. Okay, and some of them, finally, a third node are the custom constitutive models that are not available in the standard OpenSees, but are distributed with STKO as plugins. Okay, so if you want to know if something is available in STKO or not, you can consult this document to find out what is the STKO counterpart for OpenSees. Okay. Okay, so this is one node that I want to show you, and then something else. Just before starting with the webinar, is this one. Now we are in a process of creating a document for validation. Now, as you know, OpenSees is an open source software, and using an open source software has many advantages because you have all the state-of-the-art material models, element models, and so on. But it has also some disadvantages because you don't know what is an element or a material model that is there in OpenSees from a long time, so it's well tested, and you don't know what is instead a new element, something that is under development and probably is not truly tested. So we decided to create a validation manual. Now, this is still a work in progress, but we are going to put it on the website quite soon, I think for the end of this month. Basically, we took something like 50 NAFEMS test, benchmark test, and we are trying to test all the components that we have in OpenSees against these commonly used benchmarks. So I'm going to show you just some of them. Benchmark of all kinds, so for trusses, beams, as well as continuum elements, shell elements, and so on. Now I will just give you a very brief introduction. And this is quite nice because unless you're very familiar with OpenSees, and so you know what are the elements that are there from a long time, or what are the elements that are pretty new, with this document, you can understand what element you can trust, what element instead needs some more validation. Okay, this is quite important because we couldn't find any validation in OpenSees except from the very basic example that you can find on the website. Okay, so you will be updated when this document will be online. So now we can start with the webinar. So let me put it full screen. So today we are going to create this model, an existing reinforced concrete structure. As usual, not by tomorrow because tomorrow is holiday in Italy, but the day after tomorrow you will have on the website the recording of this webinar and all the support files. And in the support files you will have these basically. Well, here in building you have all the files that we are going to do today. Here in Beam, you have a simple example of one common problem that I'm going to talk about during this webinar. And under the support, you have all the PowerPoints and references that I'm going to show you. This model is based on a study that has been done in this paper. I will share it with you. So you can find all the details about this existing building here, okay? And in the PowerPoints that I'm going to show you. So here you have the model, all the plans, the elevations, all the reinforcing layout, and so on, material properties. Now don't worry, here it is in Italian, but the one that you will find on the website will be translated in English. So don't worry about that. And okay, so we can start. Now first I will try to show you how to model a frame structure like this. And then we will start adding non-linearities one at a time. So first we will start with a continuous frame model. So just columns and beams modeled with fiber cross sections. Then I will show you how to go from linear kinematics to non-linear kinematics using P delta. So we'll start adding non-linearities one at a time. Then I will show you one common problem that you have when you use fiber cross-section for beams together with a rigid diaphragm. You have a commonly known problem of having an undesired, very high compressive stresses on beams. This is something that you don't want. So I will show you with some very basic example how what is happening and how it can be solved. Then after that, I will show you how to create reinforced concrete beam column joints. This is something that probably in new design structure is not so important because you are designing the joint to behave in a certain way. But with existing structure, it can be very important to model joints because probably they are poorly designed or not reinforced at all. So it can be important to model them. If you already know OpenSees, you know that modeling a joint can require a lot of time, and I will explain you how to do this in OpenSees manually, and then I will show you a tool that we have in OpenSees and STKO that will allow basically to create beam column joints with just few clicks, so very easily, okay? So we can start by creating a new document. First of all, I'm going to create a new folder here, just to not overlap with the existing one. Example. Okay. So the first thing that we're going to do, I'm going to show you how to easily create a structure that has a quite regular grid like this one. So for example, here we have all the dimension. We are going to model everything in meters. In this document, it is in centimeters, but we're going to do everything in meters and kilonewtons. So keep in mind the consistency of unit system. Okay, so let's go in STKO. When you have to do something multi-story frame, we have something in the chat. Just a second. Oh, it's fine. Okay, so when you have a frame structure like this, so multi-story, it's easy to create first a grid of points on the base and then do an extrusion. I will show you how to do this in STKO. So starting from a from an empty file, the first thing that you can do is to go in geometry and start creating some lines, some construction lines. So first I will create this polyline here, going from 0, 0 up to this point, okay? So in this case, I can go in the top view. I can start from here. You can drop the first point at 0, 0. Then you can enable the orthogonal constraint. You can put on the X direction and you can start typing the dimensions. So the first one is 3.45. Okay, and here you have a point. Then you keep on going and you can type the distances relative to the latest point. So 3.45, 5.7, then, yes, 5.7, then 2.75, once again, 5.7, and 3.45. Okay, so this is the first line corresponding to, to this one. Then we are going to do the same with this one, okay? So once again, a polyline starting from 0, and then 3.75, 3.3, and 4.4. Okay, so now that you define these two basic lines for the grid, you can use a tool called sweep. Okay, I will show you how to do this. Sweep is basically like the extrusion, but instead of being a manual extrusion, you can extrude something along a path. Okay, for example, I want to extrude this vertex along this path. Now keep in mind that you can extrude everything in STKO, and every geometry will create something else. For example, an extrusion of a vertex will create a line or a polyline. The extrusion of an edge will create a face or a shell, which is a polysurface. And the same thing for faces. If you extrude a face, you will create a solid or a composite solid. Now, in this case, we are dealing with frame structure, so we just need to extrude vertices. So I can click on the sweep command, and then here on the top, you have all the switches for the selection. Now, in this case, I can select just an entire geometry, but if I switch off this point, this button here, let's say select geometry, I can just select some of the sub-geometries, sub-entities, okay? And just to make sure that I don't accidentally select something else other than a vertex, I can just switch off all these points in such a way that I can select only vertices, okay? So now I can select all these vertices here. I don't need to select this one because I already have this extrusion line. Then right click, and here STKO say, okay, select the spine, which is the path for the extrusion. And I select all 3 lines. So right click, and these vertices will be extruded into lines, okay? So now we'll do the same with these other 3 vertices, and I will extrude them along this other path. So I repeat the sweep command. I keep only selection of vertices. I select these 3, right click, select the spine, and I want to select all these edges, and right click, okay? So now I have all my basic construction. As you can see now, however, they are all separated from one another. What does it mean? When they are separated, even the mesh that will be generated will be separated. So for example, in this case, even if you see a single vertex, these are actually 2 overlapping vertices. So if you want something that is physically connected, you need to use a Boolean operation. Now, in this case, we have all lines, so we can use the make wire. So we select all of them, just like this, right click, and all those lines now are joined into a single polyline, okay? So this one will be the base for our floor. But actually, looking at the drawing, let me go back here. I don't need some of the beams, so I will remove them just before continuing. So I don't need. Oh, if you want to remove something, like for example, in this case, you have a single geometry. If I go here, I can select just the entire geometry. How do I remove some of the components of this geometry? I can use the subselection feature, as I showed you before. So I switch off the select entire geometry. So now I can select only these sub-geometries. And I want to remove all these beams here, while I keep this one, because this one is for the staircase. Let me check it. This one is existing for the staircase. Okay, once you have them selected, just press delete or cancel in your keyboard. Okay, so basically this one is the basic drawing for our first floor. Okay, now we can do the same. We need to extrude all the columns. Now to do the same, we go here and see the elevation of each floor. Now each floor, basically, we have only the first floor, which is 3.4 meters, and all the others 5 floors are 3.05 meters. So how do I do this? I go in front view, and I can draw another path, for example, here. And then I type 3.4 for the first floor, and then 3.05, 3.05, 3.05, and the last one, 3.05. Okay, so we have a total of 6 floors here. Perfect. Now, first of all, we need to, I go back to the full selection, and then I copy this one all over. So I use the copy command, and I copy from here to here, and so on. And the last one. Perfect. So now we have all our floors. And then I need to select all the vertices on the base, so I can use the sweep command to create the columns. So I click on sweep, I switch off the full selection, I keep on only selection of vertices, and I select all the vertices of the first floor. So I can go in the front view, I can draw a rubber band selection, and as you can see now, I have selected only the vertices of the first floor. Right click, and then I select all the edges for the spine. Right click, and now they're extruded. Okay, now I can get rid of the first floor because I don't need it anymore. So I select it and press cancel. Okay, so basically now we have all our basic drawing. Once again, they are all separated. So as we did before, we click on make wire, we select them all and right click. Okay, so we now have one single geometry. And for the sake of simplicity, we can rename it as structure. So we give it a meaningful name. Okay, now for the moment, I keep this drawing here because I may need it. The first thing that we're going to do is, this one is fine. So our structure is fine. But since we are going to create rigid diaphragms, we need the master nodes, okay? So we're going to create them. So I click on point, and I click on this one, and then I keep on adding points. As you can see here, I can repeat a command just by pressing the space bar. Okay, perfect. So we have 6 points. Now I can get rid of this line. So I have all these 6 points. Now these 6 points do not need to be separated. So for the ease of selection, you can create something which is called compound. Compound is basically a group, okay? So since I don't want to move them around one by one, I want to move them around in one shot, I can use the make compound command. So I select all the vertices, right click, and so as you can see here, now I have just one single geometry, which is called compound. And I can rename it floor master nodes. Perfect. Now I want to put them in the middle of my structure, so I draw a temporary line, diagonal from here to here, so I can use the osnap command to go in the middle. And then I select this one, I use the move command, I select this one, right click, and then I move this point to the middle of my structure here. Perfect. And now I can get rid of this line. So basically here we have two geometries, the structure, the main structure, and a group of nodes for the rigid diaphragm master nodes. So now from the geometry point of view, everything is done. I just want to show you something just before going ahead with the constitutive models. In this case, and if you look at the drawing here, we are going to have many columns that have the same cross-section, but they are oriented in different directions, okay? So now here you have two options. You either create two equal sections, but with a different orientation, so two different cross-sections, or you can use the local axis. Local axis is a tool in STKO used to orient a beam, okay? Which is what basically will create the coordinate transformation in OpenSees. Now, basically, by default, STKO tries to align everything using the global axis. So if you click on this button here, which is show hide local axis, you can see all the default local axis, okay? Now, let's say for me, they are all fine, but some of the elements, later on I will show you, they will need a different orientation. For example, the y-axis, instead of being oriented along the global y, they should be oriented along the global x. So how can you do this? I go in local axis and I click add, and I'm going to call this rotated local axis. It's a rectangular local axis. Very rarely you may need cylindrical or spherical. Most of the times the rectangular local axis is fine. Now you can pick one origin, which is not important in a rectangular local axis, so I just pick one point out of my structure. And then I want to put the x-axis pointing toward the y in such a way that the y points toward the x-axis. So I click a point here, and then I need a third point to define the normal. So the third point should be in this direction, okay? Okay, so I have it here, and then I will show you what columns need to be rotated. For example, let's say you want to rotate this column. You can go in the sub-selection. I select this line only, and then I drag and drop the local axis. Now, as you can see, the color has changed. The color was grayed out before to represent the default orientation. In this case, it is a solid color, meaning that a user-defined local axis has been assigned. And as you can see, the default one was pointing the green axis, the y-axis, along the global y-axis, while in this case, it is pointing along the global x-axis, okay? Now I just do a Control-Z and undo because I don't need it. I don't need to do it on this column. Okay, so basically up to here, the drawing of the CAD file is fine. Okay, we are done. So we can save it. I'm going to save it, an example, basic modeling. Okay, so now the next step is to create all the constitutive models and the fiber cross-section for columns and so on. Now, since in this example there are many different columns, now I don't want to waste time. I already prepared a file with all the constitutive model already assigned. So I will open that one, and I will explain you how to do a couple of them. But at least we don't waste time creating fiber cross-section. By the way, in all previous examples, in all previous webinars, we already show many times how to create fiber cross-section, okay? So you should be already aware of how to do it. And if you don't know, you can still watch the previous webinars. So I go in Home and I click Open. And I'm going to open, if you go on the building folder, you will find it by the day after tomorrow. Here you have many files, the building, then which is the basic one. And then I will show you the building with offset and the building with offset and joins. So we will create them one by one. Let's start by this one, basic building. Okay. And I'm going to save it with a different name in the example folder. Let's call it building. Okay, so basically you have the same geometry that I showed you before. So the entire structure, the floor, let me switch off this one. Okay, the entire structure, the floor master nodes, and the rotating column axis. Okay, if you want to see where this one has been assigned, you can switch off, you can switch on this one, and you can see that some of the columns have the solid color. They have been oriented in a different way, okay? Okay, so let me switch off this one. Oh, and one more thing that I've done here is the selection set, but I didn't show you how to do it. Probably I will show you. Will show you now. Basically, we need a selection set for the control node, and we will need it later on for the displacement control analysis. Okay. Now it's very easy to create a selection set like this one. The basic command is you go here, selection set, right click, add, and then STKO says select geometries or interaction that you want to include in the new selection set. Now in this case, I just want the top node, the top one of the master nodes to be the control node. So I draw a rubber band selection here, and as you can see, the top node has been selected. Right click, and I give it a name, so control node. Okay. Now I don't need to create it because I already created once, so I can delete it. And basically you have this selection here. Now selection sets are used for a couple of things. First of all, to reuse a selection. For example, in many modeling, in many situations, you may have the need to select a portion of a geometry many times. So instead of going and selecting them all over again, you can do it once, you can save the selection set and you can reuse it. For example, just by clicking here and click select. And so basically you will have your selection already there, okay? Or in some other cases, for example, for OpenSees to create a displacement control analysis, because in a displacement control analysis, you need to specify the control node, okay? And the control node should be specified using a selection set. Many other cases, for example, if you want to create regions in OpenSees, also in that case, you need a selection set. Okay, so basically the modeling of the CAD model is done. So you have all the geometries. Well, you need the interaction actually. So probably I think I will show you the interaction in the previous model because I forgot to show you. So let me save this one and let me open the basic modeling. I forgot to show you how to create interaction. So creating the interaction here is pretty easy. You just go here, you click add, and we can call it interaction for diaphragms. When you press OK, STKO says, okay, select first the master geometries. Now, in my case, the master geometry is all the control nodes, okay? So I can go here and I press select, okay? Or I can do it right from the view. So I go on the top view and I select all of them. So these are my master, right click, and then select all the slave geometries. Now I can go in the front view and I can go in sub-selection, making sure to select only vertices. And then I can draw a rubber band selection, selecting all the vertices of the floors, okay? And then I can do a right click. So as you can see, you can do them all at once because in STKO, we have an algorithm that automatically attaches the slave node to the nearest master. So for creating floors, it is perfect. You don't need to create one floor at a time. You just need one interaction, okay? Because in any case, all the slave nodes of a floor will be attached to the closest master node, which is the master node of that floor, okay? So basically the modeling is done here. As you can see, you can create a model, you can create the geometry, you can create interaction, and then the selection set for the control node. Okay, after that, you need to create the constitutive models. And so I go back to my building model. Okay, so when you have everything here, you can start with the physical property. If we go in property here, now everything has already been assigned, but I'm going to show you just a couple of them, just to remind you how to create a fiber cross-section. So for a fiber cross-section, the first steps are to create the uniaxial constitutive models. So one for concrete. Now, typically people create two versions of the same concrete, one for unconfined and one for confined. Now, this is fine if you want to do it by hand. Otherwise, we have a tool in STKO that automatically computes the confined concrete starting from the unconfined ones. And then, of course, there is another problem in an existing building. It's up to you to understand if you can consider the confining effect or not. Now, in this case, we are going to consider it. So the first thing that you want to do is to create a concrete model. Now, in this example, we have chosen a concrete 01, and we use 20 megapascals of peak strength, and then the typical values. And here you can see how it behaves. We can do a simple test just to make sure that everything is fine. We don't want to push it in tension because in any case, there is no tensile strength for this material. Okay, so this is the behavior of our unconfined concrete. Okay, then we do the same for steel. For steel, we created a new material which is under material uniaxial steel reinforcing steel, and we have chosen the steel 02. These are common used parameters. And let's see also this one, how it behaves. You can push it a little bit more. Okay, as you can see, this one is the tensile strength. Then some shape parameters. These are the default ones that you can find in the Menecotto Pinto model. And then a little bit of hardening, strain hardening. Okay, so also the steel is fine. So when you have concrete and steel, you can start creating all your fibers. Now, for the sake of simplicity, I use a naming convention here. So all the columns start with like this one, with the C, and then the dimension. In this case, it is in centimeters, but it's fine. So 30 times 40. Then here we have the rebar layout. And then I put a suffix here called fiber, because the first thing that you do is to create a fiber cross-section. Okay, now if you have seen previous webinars, you have seen that in STKO you can create a fiber either manually, or if you have a rectangular fiber section, you can use the rectangular fiber section tool, which basically allows you to create a fiber just by specifying width, height, cover, and then the rebar layout. Now, in this case, we wanted to consider the confining effect. So we just specified the material model for rebar, so the steel one, and the concrete model for cover. As you can see here, you have the possibility to choose two concretes, one for cover and one for core. Now, the cover one is mandatory. So you have to specify a concrete for the core, for the cover, sorry. For the core, it is not mandatory. If you don't choose any material and you leave it to 0, which means none, then STKO will automatically compute a modified version of the one that you assign in the cover to obtain the confining effect. This confining effect is based on stirrups, okay, in the stirrups layout and in the confining model. If you don't want to consider confinement, you can pick up one of your concrete models. For example, I choose this one, and then STKO will not try to compute any automatic confinement. Now, in this case, we want to consider it, so I put none. Okay, so this one is just one of the beams. Oh, and one note, if you're familiar with OpenSees, up to OpenSees version 3.0, the GJ parameter, which is the shear modulus times the torsional constant, was not mandatory. Was not mandatory because you could assign it here using an elastic approach in the fiber cross section, or using the section aggregator. Okay, Now in version 3.2, they made it mandatory, even if they didn't update the documentation on the website. So if you go on the website, you still see that the GJ is optional. But if you don't use it, in version 3.2 of OpenSees, you will see an error, okay? And OpenSees will tell you, don't forget to use the GJ. So always put a GJ value here, okay? So this is mandatory for, of course, for the 3D version. If you are doing a 2D analysis, it is not important. Okay, so these are the few notes that I wanted to show you. Here we have some news, because if you have seen previous tutorials, you couldn't see the section offset. I will show you later on what it is. Now, for the moment, we don't use it. Okay, so basically I did the same for every column that we had in this model, okay? So you can find it here. Here you have all the details about the different columns at the different floors and their reinforcing layout. Okay, so we have 6 kind of columns here. These are just the fiber cross-section. If you have seen previous tutorial, a fiber cross-section cannot be directly assigned to a beam, because the beam needs something else. The beam needs the beam section property. So for example, here I have the fiber cross-section for the column 30 times 40. And here I create the same thing, but without the fiber name here to distinguish it. And basically it is a beam section property that you can find it under special purpose, beam column, beam section property. And in this case, but also on the others, I decided not to use the standard integration types, because by default you have standard integration types with the Lobato, because in that case you can use just one single fiber throughout all the columns. Now for columns is fine, but if you use the hinge radau, you can specify the plastic hinge length, so it is better for the strain localization of columns. Okay, so for example, here we choose the hinge radau. We choose the same fiber cross-section, which is the one with the same name that you have here, but with the fiber suffix, both for the I, J end, and also for the interior element, okay? So we didn't consider it elastic. We just use the hinge radau just for assigning a real plastic hinge length, okay? And we did the same for all the columns, and they have been assigned to all the columns here. So this one, for example, select, has been assigned to these columns here. Okay, so if you want to know where a certain section has been assigned, you pick it, and then you click select, so that you can see what are the geometries this section has been assigned to. Okay, so basically I did the same for all the columns. And now it's time for the beams. Now, in this example, there were many kind of beams. Now, not to waste time, I just created 2 of them, so I simplified it. But if you want to be more accurate, you can just look at this document, and you will see all the documentation for all the existing beams. So if you want to be more precise, you can draw them all. Now, I did a simplification, so I used for all the deep beams, the same one, and for all these flat beams, the same one. Now, in the beams, you have, in this case, also in the beams, as you can see, I first created the fiber cross-section, and here I create a fiber cross-section for the positive bending moment. So basically, it's the fiber cross-section that I will use in the middle of the beam. Okay, so reinforcing the major reinforcement at the bottom. And then I created the same, so same name, but with M minus. So it's the one for the negative bending moment, which is the one that I will use on the beam ends, okay? Now, how do you assign different cross-section to the same beam? Well, you can use the same approach. You can use the hinge radau beam section property, which is the same thing I've done here. So the deep beam, which is 30 by 50, okay, which is these pink ones. I created this beam section property, and then I used the M minus and M minus to the I and J end, and then the M plus for the inner element, okay, for the interior element. Now here you have a problem basically. Here, what is the value that you assign to the plastic hinge length? Now, in this case, I've assigned the plastic hinge length in in an approximate way, which is the same height of the section. But of course, you can use many other equations which are more accurate. Then, of course, this is not exactly equal to the reinforcing layout that you have here, because probably here, as you can see, the section with the reinforcement on top extends for more than 50 centimeters, okay? But now I prefer, since we are doing a seismic analysis, I prefer to keep the plastic hinge length equal to the real plastic hinge, so the nonlinear behavior will be better, rather than doing it according to the real length of the reinforcing, okay? It is just a compromise, otherwise it will be a mess to create a custom model with custom cross sections all over the beams. But you can do it in OpenSees. You can still do it. Okay, so I did it the same for the other beam, flat beams. Okay, so the section at the positive bending moment, so in the middle, and the section on the other two ends, and the beam sectional property that put them together. Okay, so as you can see, this one has been assigned to all the deep beams here, and this one to the remaining beams. Okay. Now going to the element property, we could use here just one element property, because as you can see, all of them are force beam columns. Now I decided to create two of them because the beam, they have linear kinematics. While with the columns, we have a P delta. Now we will start with a linear kinematics because I want to add nonlinearity one at a time. So we will start with just by a basic frame model. Everything is continuous with just material nonlinearity. Then in a second stage, we will add the P delta effect so that you can see each component, what effect it has on the response. Okay, so we start with the linear kinematics. And so as you can see also here, you can see I can press select. So this one column element has been assigned to all columns, and beam elements to all beam elements. Okay. Now you have all the boundary conditions. Now if we move on condition, you can see them all. Now these are the typical boundary conditions that we assigned also in the other webinars, so I will go pretty fast. We have a fix on the base. If I click edit, you can see that this one has been assigned to all the nodes at the base. And as you can see, you can go here, constrain, single point, fix, okay? And then I choose 3D and UR because we are in displacement and rotation. And then we fix all the degrees of freedom, okay? Then we need to fix something else. As you know, the master nodes for the diaphragms, they will be connected to the slave nodes, but also in 3 degrees of freedom. So the in-plane displacements and the in-plane rotation. Okay, so only 3 degrees of freedom. The other 3 degrees of freedoms need to be fixed, otherwise your model will be singular. So we created also the fixed diaphragm master nodes. Edit. And as you can see, it has been assigned to all the master nodes here, fixing the remaining degrees of freedom that are not part of the rigid diaphragm constraint. Okay, so vertical displacement and out of plane rotations. Perfect. So these one are the only two single point constraints. Then of course we have one multi-point constraint, which is the rigid diaphragm. Okay. So if I right click and click edit, you can see that it has been assigned to the interaction basically, okay? Just by doing this basically. You select the interaction, you choose the perpendicular direction. In OpenSees, direction 3 means the plane is the XY, okay? So this one is the typical choice that you do for building in 3 dimensions. And so as you can see, all these violet dots here means that this condition has been assigned to the interaction, okay? Now, after that, we need to assign vertical loads. Now, in this example, I've used the standard way. So you can assign vertical distributed loads on beams. Now, the problem is that in this case, you need to do the lumping manually. So you know that this floor has a certain value and you can find a certain pressure value, and you can find it in this document. I think it is here. Yeah, here you have all the loads for every load case. And then, of course, in OpenSees, you don't have something which is called floor load. So you can create them one by one using the distributed beam load. So both for the self-weight, or also in this case, I use a name convention. So SW means self-weight of columns. And then you do the same for the floor loads, okay? Now there is I want to show you just a preview, because now this one has been created using distributed loads. Now here there is a mistake actually. This one is kilonewtons over meter. Okay, there was a mistake in the naming convention here. But we are going to add in STKO, and it will be available soon, the surface load, the floor load for beams. So pretty much as you do in Midas Gen, for example, you can just select an area of a floor, and STKO will automatically create the equivalent beam uniform load on the boundary beams, okay? It will be available soon, so just check it on the website. But for the moment, we need to create it manually. So I created them one by one here. Okay, so all the Q equal to are all the loads for the beams, okay? And then finally, we need to create an horizontal load for pushover. This one is called, okay, horizontal load. As you can see here, it is a load, force, node force, and I selected all the master nodes. Now, why do I have this value? I decided to make sure that the sum of these values is exactly equal to 1. Why? It is not important because, as you know, we are going to do a displacement control analysis. So this one is just a reference load, and the intensity of this load will be driven by the displacement control analysis. Why it is convenient to make sure that all the horizontal loads sum to 1? Because in this case, when we go in OpenSees, we can just use the pseudo time step, which in this case is the total base reaction, okay? Because in OpenSees, when you do a displacement control analysis, the pseudo time step is exactly the load multiplier. So if the entire horizontal load is equal to 1, then the load multiplier will be the entire base reaction. Okay, so that's why I used the single value in each node is exactly equal to 1 divided by 6, because we have 6 floors, okay? And so we are done with the loads. Then we can proceed with the analysis steps. Now, as usual, the first analysis step is the recorder, okay? So here, the first thing that you need to do is to choose a name. Then you choose all the stuff that you want to record on nodes, and typically we want displacement, rotation, reaction force, and reaction moments. And then here we choose section force and deformation to record deformation and forces on beams, Gauss points. Then section fiber stress and strain if you want to record stresses and strain in every fiber cross section. And material stress and strain. Now, we don't need it now, but later on I will show you that we are going to create beam column joints, and they will be created using zero length elements. And if you want to record the output of a zero length element, you need this one, material stress and material strain, okay? So this one is the recorder, pretty straightforward. Then the next step, as usual in all our webinars, you need to add all the constraints. And as I told you, we created just 2 single points constraint, fixed based and fixed diaphragm master nodes. And we have them here. So 2 single point constraints. Make sure not to forget to put single point constraints here. Otherwise, it is not sufficient to define them. You need to explicitly apply them in the analysis steps. Otherwise, your system will be singular. And then, of course, we also have a multi-point constraint, which is the diaphragm, okay? So for a total of 2 single-point constraint and 1 multi-point constraint. Next step is to create the vertical load, all the vertical loads. So we choose a time series, which is a linear one. We are doing a simple monotonic loading. And all the loads that we define from here down to here, so from number 4 to number 20, are all beam element loads. So we put them here. There are 17 in total. And as you can see, they are all the loads that are defined from 4 to 20, okay? So you should include them all of them here. And then you can run the vertical analysis. Now, let me just explain you a couple of things. Now, for this first model, we choose the static analysis, of course. We're going to do a static pushover analysis. Then for the constraint, in this first example, I could use both the plane, the transformation, or the penalty. But then later on, I will be adding the beam column joints, and they have a lot of kinematic constraint inside. So it will be a mess if you use the transformation. First of all, you cannot use the plane constraint with the joints. Actually, you cannot even use it here because you have the rigid diaphragm. So rigid diaphragm is not fine. Cannot be used with plane constraints because it is a diagonal. It's not a diagonal constraint. So plane constraint cannot be used. In this example, you can use transformation or penalty. Now, transformation works fine, but it is not general enough because when you have many constraints, like when we are going to create the beam column joints, the transformation method may not work because some constraint may overlap, okay? So it's easier to use the penalty method. Now, the penalty method has a problem. It's actually very easy when you understand it, but you have to choose the penalty parameter. Now, by default in STKO, we choose 1 to the power of 18. But then it is problem dependent. So how you choose it? I think I already explained in many examples, but I'm going to tell you again here. So you should know what is the a representative value for stiffness of your model. Now, in my case, I have the concrete, which has a stiffness of 3 to the power of 8, I think. Then it will be multiplied by the largest bending stiffness that I have in my beams, which is 3 to the minus 3. So the order of magnitude of that value is something to the power of 6. And then you should add 8 to that number. So power of 6 plus 8, okay? And so you're around 14. Now you don't need to be very strict to that value, but try to use that value. There is an explanation for that. And basically is that 8 is half of the precision of a double number. So just use that as an example. One extra thing we are working on now in putting on something in OpenSees that can basically automatically compute this value for you, because we understand that computing the penalty parameter is not so easy for people that are not expert with the finite element method. So we are going to create an automatism in OpenSees to compute this value for you. So everything else is fine. We have a sparse solver here. We use the Newton method and norm of the displacement increment for the test command. And this is very important. When you use the penalty method, you can only use something that checks the displacement. Why? Because when you use the penalty, you will have a very high imbalance. And this imbalance will never go down to a small value. So you will never converge. So you typically need to choose the displacement, either the total or the relative one, okay? And then everything is fine. In this case, this one is the vertical analysis, so we choose load control, just 10 steps, so an increment of 0.1. And then when this analysis is finished, we keep the vertical load constant and we reset the time step to 0, so that we can start with the displacement control analysis, okay? So this is the definition of the vertical analysis. Then the next step is to add the horizontal loads, okay? So once again, we choose the previously defined time series. As I said, the time series here is mandatory, but it is not important what time series you choose, because this kind of loads will be driven by the displacement control, okay? So you just need a time series just because OpenSees otherwise will complain. Okay, and then you choose all the horizontal loads that you want. Now in this case we have just one, okay, and so we choose it. In this case, it is under load because it is a nodal force. And then you go with the horizontal analysis. The horizontal analysis has the same settings of the previous, so static, penalty method, same penalty coefficients, same solvers, and so on. The only difference is that we use a displacement control. Now, displacement control, you need a selection set for the control node, which is the selection set that we created before. The degree of freedom, we are going to push this, this building along the x direction. So the first degree of freedom, sorry, this one. And then we want to push it with an increment of 0.0025 meters. And we're going to do 100 increments, okay? So we're going to displace this one of 2.5 centimeters. And we are fine with this. Now we can save it. Now, as I told you, this one is the basic model, okay? Now, I didn't want to waste time creating all the condition and all the physical properties because I want to focus on how you can model many other stuff very easily in STKO, okay? So let's say you are done with your model like this. Basically, what you have is a continuous model, okay? Fiber cross section, but continuous. You didn't have included any spring here for joints. Okay, so first we can run this analysis and then we start adding nonlinearities one by one so that we can see how they affect the response. Okay, so once you're done, you just click run. Now we can wait a few seconds. So the first analysis is fine, and now the displacement control analysis is running. Just 100 steps, so it will take a few seconds. Okay, we are done. So once you're done with the analysis, you can go in the post-processor and we can load the database. Now we are in this example here. So I can open this first model. Once you open it, STKO creates a default plot group and a default plot, which is the deform shape. I'm going to remove it because I want to see the surface color map. Okay, so that we can see what's going on. We can increase the deformation scale a little bit to see what's going on here. Okay, so this is what is happening with fiber cross-section model without any other nonlinearity. So just material nonlinearity driven by the fiber cross-section. You can see the surface map, or you can see, for example, the Gauss point plot, if you want to see what's going on at the Gauss level, or you can visualize the fiber cross-sections. Now we'll go pretty fast here because all of these features are already discussed in previous webinars, okay? So here you have many material models. Why you have so many? Because you know that you only have one concrete, because all the others are the automatically created concrete, okay? So for example, this one will be the steel. I can remove it. So all of them are concrete. And so you can visualize the stresses in every component, stresses or strain. Probably it's easier to visualize the strain to understand what's going on in terms of plastic hinges, okay? Okay, so now I don't want to focus on this so much because we already talked about post-processing in many other webinars. So let me go back to the surface color map, and I want to switch off the beam extrusion and switch on the nodes. Okay, now I want to find out what is the displacement, the pushover curve of this building. So I can select the top node, which is my control node. Then I go on chart data, extract chart data, and then I'm going to extract results on nodes. So I click on nodes, next, from stage number 2, because the first stage is the vertical analysis. I just want to extract the result from the second stage. And I want to plot in the Y data the X displacement versus the pseudo time step. Why? In OpenSees, the pseudo time step is the load multiplier. And if you remember, our horizontal load, the reference value, was exactly equal to 1. So if I use the pseudo time step here, it will be the total total force in my building, total horizontal force. So I click on next. The node is already selected, is the number 174. Next. And then I call it simply pushover. Okay, and I click on create a chart and finish. Okay, so now basically this one is our pushover curve. The only point is that we have the U, X, so the displacement in the Y data, and the time, which instead is the, as I told you, the load multiplier in the abscissa here. So as you can see, a typical pushover curve, then you reach a peak and you see softening here. So this is the basic behavior of this kind of model. Now, the second step, we are going to add P delta effects to see how it changed the behavior of our structure. And finally, we are going to add some other features. Okay, so let's go back to the preprocessor. As you can see, changing the kinematics is pretty easy. So you just go on the element formulation, transformation type, you change it from linear to P delta. Okay, just in the columns, of course. So you can save it and you run the analysis again. Now, while the analysis is running, I go back to the post-processor, I select the chart data, and I make sure to uncheck the linked to database. Now, what does it mean? When you extract that data, by default, it will be linked to the database. So that now, for example, OpenSees is recomputing, and so it is overriding this database. If I then reload it, this chart data will be updated. Now, since I want to do a comparison with the next model, I uncheck the link to database. So this curve here will not be updated anymore, okay? Okay, so now the analysis with the P delta is fine. I can just go here and click on reload. Now, as you can see, the behavior has changed. Let's see what's going on. As you can see, there is quite a difference now. Now there is a soft story here in the middle. And now we are going to extract once again the pushover curve to see the difference from the previous pushover curve. So extract chart data on nodes, second stage, displacement along the X direction, and use the pseudo time step. Next, same selection as before, next, and then we call it pushover P delta. Now this time I don't want to create a chart because we already have a chart here. So I just want to create the chart data. So finish. As you can see here, I have another chart data. Of course, you can rename them. So for example, here I just want to call it PO, and in this case, PO P delta. Now I go here and I add another chart data, which is the P delta one. Okay, and so you can see the effect of P delta, starting from the same, then when the displacement it becomes significant, you have this extra P delta effect, okay? And everybody is pretty, they know how it behaves, okay? So now I want to show you something else. So this one is another, so we started with just material nonlinearity, then we added kinematic nonlinearity. Now I want to show you something that happens very often when you have fiber cross sections with the rigid diaphragm. Probably you have seen it already on the OpenSees website. It is a pretty known effect. Is that you know that in beams you do not expect to see high normal forces, okay? So you expect the normal force to be 0 or approximately 0. Now in this case it is not like that. For example, let me create another plot group, and I'm going to create a Gauss point plot. I switch off the beam extrusion. Okay, and I want to see the vertical force, so the normal forces, okay? So P here is actually N is the actual force. I put a deformation of 0, and I want to see only what's going on in the beams. Of course, now I see that the major normal stresses are in the columns as expected. But if I switch on the beams, I'm going to see that also the beams have a very high normal stress, which is something that I do not expect. Or actually, I would not expect, but you should expect it in this kind of modeling. So if you go on plot and you click on show, You will hide all the columns, and you will see that the beams, they have a pretty high value. And this value will also reach values of about 1,000 kilonewton here, right? 800 kilonewtons. So it's a value that you do not expect. It's not actually approximately zero. Why is this happening? This happens because when the fiber cross-section of these beams goes into nonlinearity, the beam would like to expand. And this expansion is given by the shifting of the neutral axis. But then what's the problem? Since you're using a kinematic constraint for the rigid diaphragm, you are saying that a beam cannot displace in the in-plane direction. So if it cannot displace, it will generate an internal force. Okay, and this one is actually not wanted because, as you know, if you increase the normal force, also the bending strength of the beam will change. So you may very well overestimate the pushover curve of your building. Now, I don't want to show you on this example. I will show you on another simple example that you can find on the beam folder when you will find it on the website. Now, let me open another instance of STKO so that I can show you how you can solve that problem on a simple benchmark test. Okay, so if you open the file in the beam folder, you will find this model. Let me switch off the grid and I go in property. Okay, so you have 4 examples of the same model. It is a simple, simply supported beam. Okay, so the fiber, you can find the fiber cross section here. It is, I think, 4 meters. Then I split it in the middle just because I want to use the middle point as a control node for the displacement control. And then the boundary conditions are pretty easy. So at node A, so all the first node of all the examples, everything is fixed but the out of plane rotation. While on the other end, also the in-plane displacement is allowed. Okay, so you create a simply supported beam here. Now, if it is elastic, if it was elastic, you wouldn't see any, even if this one is not constrained, you wouldn't see any in-plane displacement. But since it is nonlinear, and with the concrete material model that is unsymmetric with respect to tension compression, you will see a shift of the neutral axis and consequently a shift of the beam. Okay. And then I will show you what happens, for example, in the central model, this one, which is this one, is a beam without an equal DOF. Then this other example here is a beam with an equal DOF constraint, okay, which is basically the typical example as the one that we have seen in the previous, in this building here. Is a typical case of a beam in the middle of a rigid diaphragm constraint, okay? So basically what the equal DOF in the x direction is saying is that this beam cannot displace in the in-plane direction. The consequences will be that this beam will develop internal forces, internal axial forces. Then these one are the two extrema. So this one is the lower bound, let's say. So the beam is free to expand. In this other case, the beam is completely restrained from expanding. Now you may say, yeah, but what is the reality? Well, in the reality, you can simulate it by creating a beam. Let me show you the geometry of this one. A beam here. Then, instead of assigning and applying the boundary condition on the beam itself, I created another beam, well, actually a truss in the top level here. This truss is rigidly connected to the beam. And then the constraints are applied, as you can see in the condition here, directly on the truss, both the vertical load and the constraints. And then this truss has the physical property of the slab, okay? So in this case, it was, I think, 10 centimeters, and this one was 4 meters, so 2 meters per side, okay? So we want to know what of these two is more similar to the real configuration. And then we have another choice here, which is, yes, we use the equal DOF also in this example, as you can see. But instead of using the equal dot on the middle of the beam, we choose a section, in this case, with an offset. So, for example, here I have a fiber cross-section, where I told you before, the section offset is by default equal to 0. So the beam will pass through the center of the section. And this section is the one that I assigned here, here, and here. Now, in this case, I created another section, which is a copy of this one, but with the offset, okay? So this one has a height of 500 millimeters, and then I created an offset of minus half of the height. And then this section is the one assigned to this beam, okay? So I want to know what of these three is more similar to the real solution. Probably if you have followed one of our previous tutorial, we have seen that the problem of high normal stresses generated by this example can be solved by using an axial release, okay? Now, in this example, I will show you a different approach, which is even more similar to the real solution, which is using the section offset, okay? Now, before I couldn't do it because we didn't have the tool in STKO to apply the section offset. Now, in this new version, you have it, okay? So every section, either the elastic or the fiber cross-section, has these offset fields, okay? Both in Z and Y. So if you run this analysis, you can see the results that are already in that file, in that folder, sorry, beam. And now I will show you the surface color map. And for the sake of simplicity, I'm going to switch off the extrusion and switch on the nodes. Now we want to plot the deflection versus load multiplier of the middle points. So I'm going to extract chart data, nodes. Here we have only one stage, and we choose the vertical deflection. Next, and then we choose the middle point of every beam. So I will start with the basic model, which is this one. So the first node will be the one of the beam without any constraint, okay? So let's say the lower bound. Then here we have the upper bound. So this one will provide the most soft solution. This one will provide the stiffest solution. Then the real solution will be, let's call it real, but will be the detailed solution will be this one. And then we are going to see how it behaves if I use the section offset, okay, which is the last one. Next, I call it UZ. I create a chart data and I keep multiple results. Pay attention that when you select more than one entity, you can add the results, you can create an average, you can calculate the maximum or the minimum, or you can keep multiple results. Now in this case, I want to keep them separated, so I use keep multiple results, finish. So these are the outputs. As you can see, they're very different. The real solution will be the lowest bound solution, which is the one given by not using any constraint, is the black one. So the first one here. As you can see, it is the lower bound. On the other hand, when you use the rigid diaphragm, or in this case, the equal dot, is the red one. As you can see, this one is still elastic. It didn't even arrive to, actually, it's not elastic, but it has a very high bending strength. So it will go in hardening and then eventually it will collapse. Now the real solution is the third one, which is this one, which is the green one. And as you can see, the one with the offset behaves very well and is closer to the exact solution rather than using no constraint at all, which would correspond to using an axial constraint, as I've shown you in the previous webinars, okay? So why is this happening? This is happening because basically this one with the axial curve has a very high compressive stresses. So if I go here, for example, and I change the plot group to a Gauss point plot, as you can see, when I plot P, so the axial stress, only this beam will have very, very high axial stress. This one will have actually 0. And here you can see something, because in the real solution, the axial stress is not exactly 0, but is much less than these values, okay? So this one is a simple benchmark. You can visualize it, you can test it, but it's simply to say that we are going to use the offset cross-section, okay? While in the previous example, I already shown you, in the previous webinar actually, I already shown you how to obtain an axial release. Okay, so now we can close it. So the next step that we are going to add here to solve this problem is to create section offsets. So we don't need it anymore. Go back to the preprocessor. How do you create section offsets? Well, as I told you, so we go in the, oh, before doing that, before changing the analysis, I want to unlink this chart so I don't lose it. So I go in the fiber sections of the beams. Now, as you can see, they will change here. So I keep one of them. It is not necessary to do it on both of them. It is sufficient to do it in one of them because both of them then are connected through this, this common beam property. So in this case, it is 0.5 height. So here it should be minus 0.25. Now, as you can see, all the beams have been brought down here. Now, just for clarity, I do it also on the other beam. So minus 0.25. Okay, so the deep beam now has a proper section offset. Now we do the same section offset also to the flat beam here. Now in this case, it is 0.25. So in Z, here I use minus 0.125. Okay, now also this one is aligned. Once again, for clarity, I do it also to the other cross-section, even though it is not necessary. So 0.125. Okay, so now this is fine. This is the same model, but with a beam offset in such a way that we don't have that strong axial stresses. So if I save, I run the analysis. And we are going to compare the curve, and finally, I will show you this new tool to create the beam column joints. Let's give it a couple of seconds. It's finished. Go back to the post-processor, reload it. And now we are going to extract once again the, the pushover curve. So I select this node, extract chart data on nodes, stage number 2, displacement, pseudo time step, next. This one is pushover, E delta plus offset. Don't want to create a chart data, we already have one. So finish. I just want to remove this suffix from the name so it is clear. And I go in pushover and I add the other one. Okay, now in this case it is not giving, was not so strong the axial stress as in the previous example in the benchmark I did on the beams. But as you can see, also in this case, the overall strength is decreasing. Okay, so considering the equal DOF in the middle of the beams, so the rigid diaphragm in the middle of the beams, pay attention that if you use fiber cross-section beams, you may overestimate the response of your building. Okay. Now we are fine. The last step of this tutorial is how to create beam column joints. Now, in one of the previous webinars, I already told you how to do it, how to do the scissor model, and I'm going to explain you very briefly what it is. I think you have it here in the joint model PowerPoint. So basically, one way to represent the nodes, the joint panel, sorry, is to create a rigid offset. Let me go, okay, here. Is not to do as we did before. So every beam and every column, they just coincide, they just join into the same point. In the scissor model, sorry, is this one. In the scissor model, you create rigid offsets, which are basically the same size of the joint panel size. And then you take this node in the middle, you duplicate it, and then you attach the columns joint offset to the original node, the beam joint offset to the secondary node, and then the first and secondary node are connected together using a zero length spring, basically, that is continuous in all the degrees of freedom except the two rotational degrees of freedom about X and Y. So to represent, so this bending moment versus rotation diagram will describe actually the shear behavior of the joint panel. So in this document, you have all the references. You can create external and internal nodes. It's very easy, and then you can use a typical pinching for material model in OpenSees to calibrate the shear behavior of the joint panel. Now, in the references that I will send you, you will find all the equation to compute these points. Now, for the sake of simplicity, in my example, I will show you how to do just one of them. Then if you want to be more precise, you can apply these formulas to every joint. Now, the first thing that you can see here, and if you have seen our previous tutorial on lump plasticity models, is that creating this kind of assembly here is not so easy, because you have to go here, then explode all the geometry, create all the rigid offset by hand, one by one, then you need to create equal dots. So you need to do a lot of operation for every kind of node. Now, in my previous webinar, I did it on a very simple structure. It was basically a one floor, one span structure. Now, when you do it on a multi-story building, it is not so easy. You should do it for every node, and it will take hours of modeling. Now, in this case, we created an automatism in STKO. You will see that it is very easy to create rigid joints here. You basically don't have to explode anything. You can keep your model continuous. You will assign some elements, some material to the vertices where you want a node, and there STKO will create nodes using the scissor model. So let's go ahead. Let me save this one. So the first thing that you want to do for your joint model is to create a uniaxial material, and we can call it joint uniaxial moment rotation, which will represent actually the shear distortion diagram. So you can model materials uniaxial, and we choose some standard, and we use, other uniaxial, and we use the pinching for as in the references, or you can use any other material that you want. Okay, now here already pre-calculated, but as I told you, you can have a look at those formulas or use any other formula to pick up these values. So here we have the values defining the backbone curve in terms of forces, 1.2.06, 1.27.43, and then the residual strength, which is 5.4.794. Then you have the same values, but in the abscissa. So in the rotation here, 0.0007, 0.006, 0.002, and the ultimate one, which is 0.065. Then we don't use this option here, which is used to define the non-symmetric backbone for the negative part. We're going to consider it symmetric. So we go with these other values that are not so important here, but if you want to see a description of each component, of course you have it here, okay? This is to defining the cyclic behavior. So we use some standard values, 0.21, 0.19, and 0 here. And then some other coefficient for the degradation, 0.85, sorry, 0, and 0.12, 0, and 0.96. Some other coefficients still for degradation. There are 0.31, 0, 0.34, 0, and 0.96. Then all the others are 0 except this one. Okay. Perfect. Then as damage type, we choose cycle. So when you have a material with all these parameters, unless you are very familiar with them, you may want to check it. Okay. So just to make sure that everything is fine. So let's push it a little bit and let's see how it behaves. Okay. So this one will be our symmetric behavior for our joint. Now, of course, you need to create this one for X and Y and for every node, because this kind of law depends on the node properties. Now, for the sake of simplicity, we are going to create just one, assuming that all the nodes are equal in this example. Now, in your case, you have to create many of them, but you don't need to change the geometry of your model. So this is pretty nice. And I want to anticipate that we are actually working on making it even more automatic by allowing STKO to automatically compute this one based on the fiber cross-section of the converging beams and columns on that joint. So in that case, it will be made completely automatic, but we are still working on that. In this case, only the modeling is automatic, but you are responsible for providing the proper constitutive model. Okay. So this one is the uniaxial material. Now the next step is to create the reinforced concrete joint. So joint material. And this one, as you know, is not in OpenSees, is one of those special purpose materials that I told you before. So you go under special purpose and you see RC beam column joints. And you can see here there is only one, RC joint model 3D. We are going to develop it also for 2D, but for the moment we have the general one, which is the 3D. Now in this case, we need to choose the moment rotation diagram for X and Y. Keep in mind that X and Y are local directions. So if, now in my case, this building is aligned with the global axis. So local X and local Y are equal to the global X and Y. But imagine you have a structure which is rotated. You can simply assign a local axis as I did for the columns, and you can rotate them. There is no problem. So in this case, we assume that the node has the same behavior in both directions. This is not true. So when you're going to repeat this example, if you want to be more precise, create different components for X and Y. So now we use the same both in X and Y. Now what's this? Then you have a K, which is a penalty. And as you can see in the description, this is a penalty value to enforce continuity in the other degrees of freedom, which is UX, UY, UZ, and RZ in the local coordinate system. Why? Because STKO, behind the scenes, creates a zero-length element. Now, this zero-length element has 6 degrees of freedom to join the 2 duplicated nodes. Now, 2 of them are governed by this uniaxial model. The other 3 should be continuous. Now you may say, okay, but why don't you use a kinematic constraint like an equal dot? You can't, because in this simple example in which my building is aligned with the global axis, I can, because in OpenSees, the multi-point constraints are aligned with the global axis. Now imagine I have a building which is rotated with respect to the global axis. I cannot use multi-point constraints because I should use them in a skew coordinate system, but this is not allowed in OpenSees. So that's why we choose to use a penalty approach. So basically we will create this zero-length element, and it will assign an elastic material in the other degrees of freedom using this stiffness. Now, once again, this has the same meaning of the penalty method in the analysis. So it should be a large value, but not so sufficiently large to ensure continuity of the response, but not so large to make the response unstable. So once again, you can use something like, which is, let's say, the bending stiffness of the beam with a couple of order magnitudes more. So in my case, it was 1 to the power of 8. Because in my case, I was having 3 to the power of 8, which is the stiffness of the concrete. And then the highest bending stiffness was 3 to the something to the minus 3, I don't remember. So I add to a couple of order of magnitudes and I go to 1 to the power of 8. okay? So this one is our material. Now, in the same way, we create an element property, which is the joint element. We go under model, RC beam column joint models. Now this one has the same name, RC joint model 3D element. So I choose this one, and here I just have to specify the dimension of the node in X, Y, and Z. Once again, in this first attempt of creating the joints, we decided to let the user specify the physical dimension of the joint. Now, in the next step, we are going to make it also automatic. So STKO will understand the size of the beam column joint directly from the size of the fiber cross-section converging in that node. Now, for the moment, you have to specify it. In this case, for the sake of simplicity, I'm going to consider an average size because I want to use the same joint for the entire model. So typically, the size of my beam cell columns are 30 centimeters, 50 centimeters, or 1 meter for this kind of beam. So I do, let's say, a 0.4 everywhere. It is not correct, but if you want to be more precise, you can create more joint elements, of course. Now, what I want to show you is that once you have created joint materials and joint elements, the only thing you need to do is to select the vertices here and drag and drop them. You don't need to change your model. So for example, I go in the front view, I switch off the full selection in such a way that I can select only vertices, and then I select all of them, paying attention not to select the master nodes in the middle, okay? So basically I selected all the nodes, and then I drag and drop the joint material, and then I reuse the previous selection, and I drag and drop the joint element. Simple as that. So when you have done this, all your model, even if your model is continuous as it was before, when we are going to write the TCOL file and run the analysis, you will see that STKO is actually duplicating this node and creating rigid offsets between the beams and the columns, okay? So let me save it, and I will run the analysis. Okay, while this is going, I want to make sure that I unlinked this one. Yes, it's fine. Now we're going to see what is the effect of considering, at least in this case, the beam column joints. As you can see, it is a little bit more non-linear than before, but this is still fine. Here it is having troubles. Okay, probably I changed something because before, in the example that you have in that file, it is running till the end. So probably I changed something here, I don't remember. Let me see if it was the horizontal analysis. I should be fine. Anyway, if you open the output of the file that I already computed, the beam column joints was going through the end. So probably I used wrong values in the pinching material, but it is fine. Let me reload this one. Now, as you can see, when you reload it, you can see actually the offsets of the beams and the duplicated node here in the middle. And it is more clear if I switch off the beam extrusion, okay? Now every node basically has been correctly duplicated. So here you have two nodes. For example, if I select this one, I don't have only one. I have one node, another node, which is the duplicated one, and an element, which is the zero length element between these two nodes, okay? So two nodes, one connected to the column, one connected to the beams, and the two of them are connected together using the scissor model. Okay, and then of course in these blank spaces here you have a rigid link constrainer. This is a rigid body constraint, so no element has been drawn here. Okay, so I keep on selecting this one, and I try to export the pushover data. It should be almost the entire curve. But if it is not, I will open the results of the material that is already there, because probably I made some mistake in the material properties, but it is fine. So stage number 2, displacement versus pseudo time step. This is offset with joint. And I'm going to add it here. Okay, no, now in this case it has stopped before, but probably I made some mistake. I will open now the real database. So let me remove this one. Oh, no, well, of course I can recreate it. Probably I made some mistake here. Let me show you in the definition of the joint uniaxial material, okay? So if you want to make sure, just open the file that I have here, and here you will have the real value, which is this one, with offset and joints. Okay, now I will just open the output coming from the pre-computed model, which is here. Surface color map, okay. As you can see, all the joints are there. I switch off this one, I switch on the nodes, and I select the top node. And I extract the data. So on nodes, stage number 2, displacement along the X versus time step. Now I create a chart because I accidentally deleted the previous chart. So this one is PO, P delta, offsets, and joints. So finished. This is the full curve. And then I keep on adding all the previous. So I have the simple pushover, which was this one. Then the pushover and P delta, which is this one. Then the pushover P delta with offset, which was the second one. And then when we have the same curve but with the joint, we see a slightly different result. Now basically the response here as a lower lower peak, because the joints have been activated before the soft story in this kind of in this piece of building. Okay. Now, if you want to visualize what's going on inside the beam column joints, as I told you before, here in the recorder, we have been using this output request, which is the material stress and material strain. Okay. This was useful for the for visualizing then in a Gauss point plot here the output of the scissor model. So when I'm here, I switch off the beam extrusion. Now by default, here I have the section forces, but I can choose material stress or material strain, and I will see the stress and strain in the zero length elements. Now to visualize what is the most damaged one, I typically use material strain. So where the strain is larger, and in particular in the rotation about the local y-axis, I can see where the nodes have been activated, okay? So you can pick one of them, for example, this one. And we can try to export the moment rotation curve, which is actually shear versus shear deformation. So extract chart data. Now in this case, it is a Gauss point. Okay, so we go in extract from Gauss point. Next. Stage number 2, which is the pushover analysis. Now in this case, we want to plot a result versus another result. Why? Because we want to plot in the abscissa, we want to plot material strain, and here we want material stress. Now we have 6 components, this 6-1. Now don't see about, if you see here, you see the typical notation of a tensor, because STKO, when sees something which is called stress or strain and has 6 components, STKO understands that it is a stress or a strain tensor. But the point is that it is not that in this case. In this case, it is a simple zero length elements that has 6 degrees of freedom, 3 for displacement and 3 for rotation. But since OpenSees has called it strain or stress, STKO thinks it is a tensor, but it is not. So the 5th component is the rotation about the y-axis. That's why I'm going to select this one. Okay, 5th component and 5th component here. Next. So Gauss point 0, as you can see here, Gauss point 0 of element, this one is a zero length element of the first database. Next, and then we can call it joint moment rotation. Finish, and this one is our model, okay? So the first stage in hardening, then it just started a little bit of softening. So probably we can push it even more to see some softening here, but it is fine for the sake of, for the aim of this tutorial. Okay, so basically in this tutorial you have seen how to start from a simple building, modeling this one in the CAD environment of STKO, how to start with a simple model using fiber cross sections for beams and columns, everything connected, and how to add nonlinearities and details one by one. So first of all, the rigid diaphragm, then how to remove the problem of the rigid diaphragm using either an axial release, as I told you in the previous webinar, or in this case, how to use the beam offset. Then I have shown you how to change from linear to P delta kinematics, and finally, how to create rigid joints. And as you can see, using the automation tools that you have in STKO, and in fact, we are working a lot on that, can speed up the modeling a lot. So in this case, you didn't have to change anything in the model, just assign a couple of more material models, and the output is a model with this scissor model. And doing it by hand, trust me, it takes a lot of time. So we're done with this webinar. So if you have any question, we have, let's say, other 10 minutes for questions. So please, if you have any question, go ahead. Thank you, Nicola. Well, of course, thank you everyone for joining. Here we have a question. In case of RC walls, do you suggest any model inside STKO? Yes, for RC walls, actually, we did some previous webinars using shell elements, and I explained how to use shell elements with embedded reinforcement. Just a second, I finished it with this answer, and then I go to the next. So RC walls, you can either do it with shell elements, and we already have a webinar for this. And of course, you can use more simplified models using equivalent trusses, both for RC walls or infills. And this will be the topic of one of the next webinars. Okay, so next question. How to ensure the rigidity of the joint structural detailings. Okay, so let me go back. Here we have someone saying how to ensure the rigidity of joint structural detailings. Well, as I told you, let me go in the previous processor. The rigidity of the other degrees of freedom that are not involved in the nonlinear modeling of the joint. So the other 6 degrees of freedom, as you can see it here, joint material, can be ensured using this penalty parameter. As I told you, this one should be, actually depends on the properties of the converging elements and beams. So how do I do it? Since this one basically will be in series with the stiffness of the beam, you can choose a value which is, let's say, a couple of order of magnitudes more of the higher than the beam bending stiffness, for example. Now, in this case, my concrete model was as a stiffness of 3 to the power of 8. Then the largest bending stiffness of our beam, moment of inertia, was something to the power of -3, or -2, sorry. So it was to the power of 6, and then I have 2 order of magnitudes, okay? Now it is sufficiently stiffer that the one that will deform in that degree of freedom will be the beam, okay? Is there any criteria to locate the master node? Well, of course, it will be the center of mass. So you either need to compute it, or you can place it in the middle if it is a good approximation for you. Keep in mind that one of the main automatism that we are creating is the one for the diaphragm. As we've seen now, in this case, you have to manually create the master node. And as Gonzalo was asking, how do you place it? So you have to find this location by hand, you have to draw it by hand, and you have to fix the remaining degrees of freedom that are not involved in the rigid diaphragm. Now, in the next version of STKO, we are going to add an automatic definition for the rigid diaphragm that will do everything, all these steps for you, okay? Or how to do modal analysis. Of course, actually, now unfortunately we don't have time now. It is very easy. But if you want to do if you want to know how to do modal analysis, we have one of those topics in our forum. Okay. So let me show you, for those of you who is not aware of the fact that we have a forum. Whenever you have questions that are probably already answered, you can go here, support and training, support. You can go in the STKO forum. And one of them was modal analysis. I think it was in the analysis or scripting interface. Let me see. And then there is something about analysis eigen. Okay. Here people were asking how to do modal analysis, and then we answered. And then we have some tools to do a mass summary. It is in one of these webinars. I think the scripting interface. But I suggest you to have a look at the forum, because, okay, here, modal analysis plus mass participation factors. Here someone was asking, how do I get all these outputs from OpenSees? Well, OpenSees doesn't give you, for example, a mass summary, but here we explain how to create a custom TCL file that you can place inside STKO to give you an output like this. So an out in text files, all the requested modes and all the participating masses, okay? So please have a look at the forum, because many of your questions probably are already answered there. Okay, another question. STKO picks the near rigid diaphragm node, which is okay for the regular structure, but what would be in the case if we have irregular structure? It might be possible. The near one is from the upper story. No, no, it is not possible unless your structure is inclined with respect to the global Z. Because the shortest path is always the one on the same plane, okay? Well, actually, it may happen. Actually, it may happen if the master nodes are not aligned into a single line, okay? So, for example, let me see if I can annotate something here. So let's say this one is two slave nodes of a floor, and here you have the master. Then you have a second floor, which is here, here, and for some reason, the master is here, okay? Then in this case, yes, this one will be nearer to this master rather than to this one. Well, in this case, if you have such a cases, you do not create just one interaction for everything. You create one interaction for this one and one interaction for this one, okay? So basically what I told you before, that STKO couples the slave to the nearest master, it does so only inside the scope of one interaction, okay? So if you do two interactions separated, there will be no problem. Now, in my case, where the master is always aligned, like this, the nearest master will be always on the same plane, okay? But yes, of course, if you have an irregular structure, do many different interactions, one per floor, if you want to make sure. How can we calibrate the coefficient for degradation? Actually, you can find everything in let me clear everything here. You can find everything in the references that you will find in the support folder. Okay, you will find it by the day after tomorrow on our website, and you can find it everything in this reference here and the reference therein. Okay. The recorded webinar, yes, we will see you will see the recorded webinar will be on the website. Just a second. If you've lost the first part of the webinar, you can find it on our website, and more specifically here. I will show you. Whenever you miss a webinar, you can find it under support and training, e-learning courses. And here you have the upcoming webinar. This one is this one. And the previous one will appear here. So by the day after tomorrow, you will find the current webinar here with a link to the content and files and a link to the recording on our YouTube channel. Okay. How the reinforcement slip can be considered in the model? Yes, with additional zero length tab. Well, actually, you have two options. Someone preferred to lump everything into the scissor model. So if you have some equation that allows you to put here in a lumped way both the deformability of the joint panel and the bar slip, you can do it here. Otherwise, you can use, instead of using a beam section property like this one, for example, which is simply an intra-out beam, you can use the injet beam. So you create extra zero length, and then you create a special purpose. Where is it? Special purpose injet beam material, where in the middle you can place the original beam element like this one, and on the two ends, for example, in the end near the joint, you can place a rotational springs that account for reinforcement slip. Okay, then we have another question. Okay, the last question is, why offset is assigned only to the bottom story beams, not to all beams? No, it's assigned to all the beams, the offset. I just was zooming here, but it is assigned, as you can see here, to all the beams. When I was showing the effect of an offset, I was just focusing on the first floor just to show you how the graphics updates accordingly. But since this section, for example, is assigned to every beam, all of them will be affected by the offset. Select. Okay, so all of them will be affected by the offset, as you can see here. Okay, so thank you everyone for joining this webinar. So as I told you, we'll find everything, not tomorrow, because here in Italy, tomorrow it will be holiday, but you will find it by the day after tomorrow. Both the contents file, everything we have done here, and the video recordings. So thank you everyone for participating to this webinar, and hope to see you in the next webinars. And don't forget to visit our forum. Many of your answers probably are already answered there. Okay. So thank you, everyone.